Welcome, everyone. This is Greene coming to you from Columbia University in my office in the physics department here. Welcome to this live stream from the World Science Festival. And today we're going to be talking about a subject that's near and dear to my heart and to the heart of many theoretical physicists. And I do emphasize theoretical for the most part for reasons that many of you already know and would become clear in our conversation. And that is the subject of unification, the subject of putting together gravity and quantum mechanics into a unified framework that would allow us to blend together our deepest understanding of physics that has emerged over the course of many, many decades, really about a century or so during the early part of the 20th century when these ideas first bubbled up. And the conversation today will be with Juan Maldacena, who is really one of the great leaders of the field, tremendous impact across the board. So we'll spend some time talking about the issues of how difficult it is to put gravity and quantum mechanics together, why that is, how an approach that many of you know of, perhaps through popular books or television shows, maybe some I've been involved with, called string theory, may well be the answer that we have been looking for, but there are issues that need to be resolved. And we'll talk about what some of those issues are and some of the amazing aspects of the theory that have come to light in the last 5, 10, 15 years that have really convinced us that this approach is mathematically rich and has the capacity to give some dramatic revolutionary insights into the nature of the world, the nature of reality. So let me bring in Juan, who is the Carl Feinberg Professor in the School of Natural Sciences at the Institute for Advanced Study. He has made tremendous contributions across the board in string theory, quantum gravity. We'll talk about perhaps his most famous discovery, which is called the ADS-CFT correspondence, which relates to a stunning idea in physics called holography, or the holographic principle. And perhaps we'll even get to a result that puts together the ideas of wormholes and quantum entanglement, which goes by the cryptic name EPR equals ER. So let's bring Juan in. Good to see you, Juan. Where are you at the moment?
Yeah, nice to see you. I'm here in my office in Princeton, New Jersey.
And that is at the Institute for Advanced Study.
At the Institute for Advanced Study, yes.
Yeah, and of course, as many in our audience will know, that's where Einstein spent many decades of his life, the last decades of his life. And he was intent on finding what he called, and what we call in a somewhat different use of the terminology, a unified theory. Our way of framing it differs from Einstein's, of course, because Einstein was thinking of putting together gravity and the electromagnetic force. We want to put together everything, including quantum mechanics, which Einstein had his own issues with. But this modern framing of trying to have this unified description of gravity and quantum mechanics, is there any chance that we're asking for too much? Is it possible that we just have these two descriptions of the world, one for the big stuff, one for the small stuff, and we just have to live with it?
Well, I don't think so. I mean, the world is one thing. We divide it into big and small, and it has to work together. And the other point is that now gravity is important for big things, but earlier in the history of the universe, the whole universe was much smaller, and gravity was still important. And if we continue going back and back, it reaches a point where both gravity and quantum mechanics are important at the same time. So if we really want to understand the beginning of the universe, we are forced to this question of trying to put together gravity and quantum mechanics. I would say that this is the biggest practical question. Let me say practical in the sense of scientific and in terms of curiosity of trying to understand how the universe began. That is the main question why we study quantum gravity. So trying to put together gravity and quantum mechanics.
And, I give a similar answer when people ask about, why it's important to put gravity and quantum mechanics together and why we think that there has to be some sort of unified theory. Black holes is another domain that we'll probably spend a little bit of time talking about. Presumably you'd throw that into the mix as well as an arena that requires these two theories to come together.
Yes. Black holes. It's another situation, especially in the interior of black holes. So in the interior of black holes, again, space-time collapses and becomes small in some way, and quantum mechanics and gravity both become important.
And
If you're
so, yeah,
outside
so
the
if we
black
ever,
hole, yeah, if you're outside the black hole, then those effects are very small, especially for the black holes that we see in the sky.
and so, I mean, in principle, you and I could have just crossed over the event horizon of a black hole, at least in some incarnations of our understanding, and we wouldn't have even known it, because if the black hole is big enough, the effects at large
Right,
distances
right.
are not significant. But if you want to understand the center of a black
Yeah,
hole,
yeah. In the interior, it's a different story. That's right.
yeah,
So if we are falling, for example, into the black hole that is at the center of the, the galaxy that appeared in the picture in this famous black hole picture,
M87, yeah,
87, yeah. So that would take us maybe an hour or a few hours to get into this singularity. So
right. So hopefully we haven't just crossed over, but if we have, this live stream will abruptly come to an end in roughly an hour or so. So you're right, of course, that it's a human artificial division between what we call big and what we call small, but it certainly has been a fruitful division, because we've done pretty well at describing these two realms when we think of them as independent of each other. So let's start with the big, where Einstein really became Einstein, with his general theory of relativity. Just give us a thumbnail sketch of how Einstein wants us to think about gravity, the force that's most relevant for big things.
Well, the crucial idea is to think as gravity as being a consequence of the curvature of space-time. So the idea is that space-time is like a medium that can stretch and deform, and that when we have gravity, it's reflecting that deformation of space-time. So, for example, the big Earth deforms the fabric of space-time and makes clocks run at different speeds, at different heights, and that's what the deformation means in particular. And that deformation sort of causes us to want to go down in what we call the gravitational field. But so that's how Einstein views space-time. And this theory, of course, has many interesting consequences. Perhaps the two most famous and important ones are that the universe is expanding and that black holes can exist.
And so Einstein developed the general theory of relativity before he got to the Institute for Advanced Study. That was when he was still, in Germany. Finished the theory in 1915. And of course, I think, as most in our audience knows, Einstein's theory has been tested to fantastic precision. I mean, we still see tests coming, in the last few years, right? I mean, gravitational waves. I mean, were you among those who thought that gravitational waves would ever be detected? I certainly would. I was not in that camp. I thought that it was a fool's errand.
I've heard about gravitational wave detectors throughout my career. They were first building them. They would say, well, they are not sensitive enough yet. We'll have to make them more sensitive. And I thought that we would still get a few more iterations of this. But yeah, it was wonderful when they actually saw them.
Yeah, and you already made mention of the fact that we finally now have direct images from the Event Horizon Telescope of black holes. So
yeah, that's right. Yeah, and these gravitational waves are coming from collisions of black holes, and they agree in great detail with the predictions of Einstein theory. So it's one. So not the most interesting aspect about detecting gravity waves was where those gravity waves were coming from. That they were coming from very massive black holes, and are giving us the best, I think, probe of the geometry near the horizon of black holes.
Yeah, absolutely. Now, it's curious, just as a side note, that Einstein himself was quite skeptical about the existence of black holes. There are papers, I don't know, in the 30s or maybe early 40s, where Einstein tried to argue that black holes were some very special mathematical feature of the general theory of relativity, but you'd never actually realize them in the real world. And similarly for gravitational waves, he was definitely on the fence about whether he even thought that they were a real implication of the general theory of relativity. So, I mean, what's up with the great genius not trusting the implications of his own theory?
Well, the theory is based on a beautiful idea, and the equations are relatively simple, but it's actually quite difficult to interpret the solutions of these equations. And then they have surprising solutions, like the black hole solution, which took many years to be properly understood. And it's quite interesting to understand the history of classical black holes. It took about 50 years to properly understand the classical geometry of black holes. And of course, there was the key work of Penrose and Hawking and others that really clarified a lot our modern understanding of the classical geometry of black holes.
Yeah, I guess Penrose, really was a turning point in our understanding of black holes, because using mathematical methods that most physicists were not familiar with, getting away from the intricate small-scale local geometry to the global topological properties of the space-time, he convincingly argued that black holes should be a ubiquitous feature of the world.
So they form generically, not in simple spherically symmetric situations and so on.
Yeah, exactly. So here we have this beautiful theory that even goes beyond Einstein's own expectations in terms of its capacity to describe real things out there in the real world, the general theory of relativity. Let's turn to the other end of the spectrum, which is quantum mechanics. And, some of our audience will know, Einstein wrote the first or perhaps the second paper on quantum mechanics. And that's the paper that he got the Nobel Prize for, the photoelectric effect. But again, was not happy with how that theory developed. I mean, where did his discomfort come from?
Well, quantum mechanics is a probabilistic theory. So it's a theory where you don't know exactly what's going to happen, even if you have perfect knowledge of the initial state of a system, as much as you can possibly have, then you can't predict the result of future experiments. And this is what bothered him. It seemed to him that quantum mechanics was an effective theory, and then there would be a more fundamental theory underlying quantum mechanics. In the same way that, let's say, in thermodynamics, we have, for example, notions like entropy, like heat, and so on, that come from more fundamental description. And and this is what I think bothered Einstein, to think that nature at the fundamental level would be quantum mechanics. And it's I would say that it's a bother that maybe some people still share. I'm not sure people are completely comfortable with quantum mechanics. I mean, we all know what the rules are. Einstein, of course, understood what the rules are for quantum mechanics. It's not that he just philosophically didn't like the rules and thought that there might be some deeper underlying reality.
And there may be, right? I mean,
there might well be, yes.
Gerard Tufte, another Nobel laureate, has certainly spent some time trying to develop what that underlying theory might be. But, it's interesting, as you go from one generation of physicists to the next, things that were so problematic, philosophically speaking, to an earlier generation, the next generation grows up with the ideas. And presumably because of that, they don't have the kind of resistance. So what becomes, in the early days, what is so problematic for people to accept, the next generation just kind of shrugs their shoulders and goes forward with it. I mean, of course, you've grown up with quantum mechanics completely. Right. Do you have any discomfort with the theory at all?
I do. But of course, I learned the rules, and I learned that the rule is to shut up and calculate. Don't ask these questions, and that it hasn't been so far very productive to ask these questions. Though that there was the wonderful work of Bell and Bell inequalities that are basically based on these questions. So I think I'm still somewhat uncomfortable with quantum mechanics. I felt as I was studying physics that I understood everything. I understood electromagnetism, classical physics. When I got to quantum mechanics, I felt I stopped understanding completely. Stopped getting, this more intuitive understanding.
Yeah.
I could follow the mathematics. I could understand the mathematics, but...
I have a question along those lines, though. When I took quantum mechanics as a undergraduate physics major, they did not mention the word entanglement, something that we'll talk a little bit about later on. When you took quantum mechanics, was entanglement part of the curriculum?
No, it wasn't.
Yeah.
It's interesting how it shifts. I think now it's probably an important part. It's maybe one of the first few things people learn.
Yeah.
And it's because it has really, its importance has grown. I think we are just applying quantum mechanics in a new way now. So I guess when quantum mechanics was first invented, okay, so it was applied to understand atoms and chemistry and well, of course, subatomic particles and so on. And that focuses you on some aspects of quantum mechanics. And certainly entanglement is part of that, but not crucial. Now we are in the time where people are thinking about complex quantum materials. They are thinking about quantum computers and things like that, where entanglement is fundamental and very important for understanding how things work. So
it's interesting, though, that Schrodinger, way back in the late 20s, early 30s, said something like, entanglement is not a feature, it is the feature of quantum mechanics that distinguishes it from a classical worldview. So even back then, there were some of the pioneers of quantum mechanics who knew that entanglement, this idea that widely separated objects, particles, so to speak, can act as though they're next to each other, that idea was at the heart of quantum mechanics.
Yeah, no, it definitely was recognized. It was recognized by Einstein, as the famous Einstein-Podolsky-Rosen paper that you mentioned before. But it was a thought experiment. So it was mainly, for them, it was mainly a feature of quantum mechanics as a thought experiment. Now it's reality, right? There are devices where this is important.
Yeah, I mean, once you harness something and you start to apply it, it takes on sort of a different ontological status in terms of it being actually real, being really out there.
Right.
Like with general relativity, quantum mechanics has been tested to incredible accuracy. I mean, I like to quote, the calculation and the measurements of, the electron magnetic moment. I mean, it's just an insane agreement to many, many decimal places. I don't know, 10, 11, 12, 13 decimal places, something of that sort. So there can be little doubt that quantum mechanics is telling us something real about the world, however strange it might be. Probabilities, entanglement, all that stuff. There can also be little doubt that general relativity is telling us something real about the world through, going way back to the observation of the bending of starlight by the sun. But, as we mentioned, gravitational waves, black holes, and so forth. What then is the issue? I mean, why is it hard for these two theories to play well together, to coexist?
Well, as they are currently understood and tested experimentally, they apply at different length scales and for different objects. So we never apply them at the same time.
Yeah.
And so gravity is what we normally call the field theory. So it has the geometry of space-time is something extended. And as you go to shorter and shorter distances, there are these sort of fluctuations of space-time that, according to the classical theory and our understanding of quantum mechanics, we expect that the interactions between those small fluctuations becomes larger and larger as you go to smaller and smaller distances. And so that means that at very short distances, quantum mechanics and gravity should have some trouble working together. These distances are much, 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 much smaller than the distances we can measure today with our biggest particle detectors, with particle accelerators, our sort of most powerful microscopes. Yeah. So they're super tiny. So we don't have any experimental contradiction or problem. So the only problems are, if you wish, theoretically, if we try to extrapolate the equations backwards as to the beginning of time, we have a problem because of this issue, or to the interior of black holes, where again we have a problem according to this. And so we would like to have a more complete understanding of nature. So at some level, it's a theoretical question. We have two principles that we have of general relativity and quantum mechanics, and we want to put them together into a single theory. So, and the hope would be that the problem is constrained enough that the theory would be unique, or there wouldn't be too many possibilities, and hopefully it will have some experimental consequences that we would be able to check. I mean, that's the general idea of
I mean,
trying to
if we put some numbers into what you just said, I mean, if we go down to that tiny length scale where the problem theoretically would arise, the so-called Planck length, roughly 10 to the minus 33 centimeters. If you compare that, as you say, with the distance scales that we can reach with our most powerful microscopes, which are powerful accelerators, what can we reach? I don't know, 10 to minus 18 centimeters, I don't know, something.
Yeah, that's right. So one way to think about it is to think about the distance scale in terms of powers of 10, right? So we have to go some distance in powers of 10 to get to the smallest distance we can measure today. And we have to continue the same distance in powers of 10 to get to the Planck, that smallest distance of quantum gravity.
Right. So that's an audacious problem to face as a theorist, right?
Yes, it's a wild extrapolation. It might be that the world is not quantum mechanical at those scales, that there is something completely different. That's certainly a possibility. So the game is to just assume that, try to take the principles we have and come up with the simplest generalizations that puts together these principles. Now, nature might choose to do something else, or
I mean, it's fun to ask you these questions because they're often the ones that people try to put me on the hot spot or the hot seat when I'm talking about these ideas. So I'd love to hear, how you handle them as well. Is it, a fool's errand? Is it a mistake as a theorist to spend so much effort trying to leap, say, 15, 16, 17 orders of magnitude when in distance, going to 16 orders of magnitude smaller than we have any experimental input? Is it a mistake to make that wild leap to try to figure out how to put gravity and quantum mechanics together? Is it simply too early in the history of science to do that?
Well, it might be. We don't know. So if the problem was very unconstrained, in the sense that you found lots and lots of different solutions and anything goes and you could modify the rules we have in any possible way, then I think then it would be. So the reason for thinking it might not be is if you don't find many consistent ways of modifying the rules that we have to put these two things together. That I think is one way in which you could think perhaps you might find the answer. So I think right now the goal is to find an answer. So a theory that puts together gravity and quantum mechanics. And even there, I would say we don't have a complete satisfactory solution. So of course, string theory is very exciting, but there are questions we don't understand, even using string theory, like the beginning of the Big Bang.
Sure. Well, let's get into string theory since you mentioned. I think it's a natural segue to do that. String theory as a potential solution. I was a graduate student in 1984 when the first, if you will, modern breakthrough for string theory happened. The famous Greene and Schwartz paper, different Greene, no E on the end, Michael Greene, not me, paper. Where were you in 1984?
I was in high school. Yeah.
You're in high school, right? So
I didn't know about this.
Yeah, right. So you presumably weren't following any of this stuff back then, not quite that precocious. Yeah. Go ahead, please.
Yeah, string theory is really a theory under construction. So we know some aspects of the theory, and we don't know other aspects. So,
for sure. I mean, and I'd love to get into a little bit of the detail. And if you don't mind, if we could do a brisk walkthrough of the ideas from a historical standpoint, I think that's a reasonable thing to do, because there are various people who are watching this who may have followed string theory at this or that moment in the development, maybe dropped out, perhaps heard something from one of the detractors out there in the world and got sort of turned off or something. So if we go back to 84, I mean, the basic idea of string theory is little vibrating filaments, vibrating loops that, unify things in the sense that all particles arise from the same idea, the different vibrational patterns of a vibrating filament, a little tiny vibrating filament. But from the question of how string theory resolves the problem of putting gravity and quantum mechanics together, I often say that it kind of gives you a shortest distance scale. You can't go smaller than the smallest ingredient in the theory. And if the size of that ingredient is on par with the size at which the problem emerges, you kind of cut the problem out of reality. Is that how you describe it, or what's your way of giving a brief idea of how string theory resolves the tension?
Yeah, that might be a way to say it. Maybe perhaps, well, I would say it's slightly, well, I would say some other thing, might be
Yeah.
perhaps a little too technical, but
No, go
it's
for it.
some analogy with the theory of weak interactions. So when the weak interactions were first discussed, it was through the so-called Fermi theory. It was a theory similar to GR in the sense that general relativity, in the sense that as you went to theoretically, you could predict that as you go to shorter and shorter distances, the weak interactions should become stronger and stronger. And that theory predicted that the weak interaction should become very strong at the distances we currently are exploring with the particle accelerator to the LHC. Should become very strong. But then a theory was developed for the weak interactions where something new happens at this slightly smaller, slightly lower scale, lower energy scale, that there would be new particles, the W and Z boson of the weak interactions. And those were discovered, in the 80s. And so what happens is that above those energies, the theory becomes, it's weakly coupled, and the coupling continues to be more or less constant. And then that theory could make sense at even shorter distances. And in string theory, something roughly similar happens in the sense that there is a new scale, which is the mass of the first excited state of the string. And then after that scale, the nature of going to short distances changes. We don't just have gravity, we have some, let's say, stringy version of gravity or something else.
Yeah.
And then the theory can be weakly coupled beyond that, and exactly what distances mean below this scale is unclear. And so you could say in some sense that's the shortest distance. But yeah, so that's a historical comparison, let's say, between how string theory modifies gravity and how the modern theory of weak interactions modifies the Fermi theory.
Right. So you're saying, much as in the weak interactions, new particles and new physics comes into play right when there would have been a problem.
Right. Wait, it's actually before. So I wanted to emphasize, at least in weakly coupled string theory, it's before slightly before there is a problem, there is a modification. Exactly. And this is important because then it gives a theory that is weakly coupled. So it's analyzable through simple methods.
Right. And those simple methods, of course, are what we call perturbation theory.
So that's the string theory of the 80s. So that's
exactly. So we'll go into the 90s and beyond very shortly, but just to sort of emphasize that point, you mentioned the mass scale, the first excited state of a vibrating string has a certain amount of energy. In mass, that's about 10 to the 19 times the mass of a proton, just to give people a feel that we are way, way beyond any of the energy scales, much as we described before, that were way smaller than any of the distance scales that we can probe. So these are just theoretical ideas. Nevertheless, on paper, they seem to work.
Right. I would like to mention something that, also related to the history, that string theory really did not start in 84, but it started earlier, trying to understand strong interactions. Trying to understand strong interactions in the late 60s. And the motivation was really experimental, in the sense that people in particle accelerators observed objects that behave like strings. And these are real objects. So there are some real objects that you produce in particle accelerators that really behave like the relativistic strings, very similar to the strings that we have in string theory. So now we view them as tubes of color electric flux. So in the theory of the modern theory is the theory of quantum electrodynamics, but that's an example of a theory. That's an example of relativistic strings. So the strings we're talking about here are not a complete, thing that does not exist in reality. There is something in reality that is somewhat similar, and these strings are an extrapolation of further theoretical construction based on an idea that on strings that really exist.
Yeah, absolutely. I mean, it is important to recognize that these ideas didn't just pop into people's wild imagination. They were motivated by data in the 1960s, for sure. But the amazing thing is, and this is a point that Ed Witten does still emphasize, but he emphasized it really forcefully back in the 80s when I was a graduate student. He emphasized that you start with this theory of vibrating filaments, of vibrating strings. And when you analyze that theory, you find a vibrational pattern that has just the right properties to transmit the force of gravity, the so-called graviton particle. And so if you didn't know the general theory of relativity before you knew string theory, at least in principle, a sufficiently clever person could have extracted the general theory of relativity out of string theory. I mean, that's
yeah, no, that's pretty amazing. Yeah.
You know, and so it does give you some sense, you know, both from the experimental motivation early on and then from the theoretical qualities of this theory of vibrating strings, that you can't help but feel you're going in the right direction, you know. So that was sort of
Right.
Now, of course, you have to make contact between any proposed theory and things, hopefully, that you can observe with the technology that you have at hand. And one of the issues that made that difficult, beyond what we've already mentioned, that the theory really flexes its muscles, shows its true colors in tiny distance scales, large energies, is that the theory has mathematics that tells us that there should be more spatial dimensions than the ones that we know about. I mean, I found this incredibly exciting in the 80s as a graduate student, especially because I came to the subject from a more geometrical mathematical side of things. And once I saw that higher dimensional spaces and all of the wonderful technology of Riemannian geometry and topology that all had a home, I was hooked from that point of view. But when you learned that the theory had extra dimensions, was that an exciting idea, or was it like, whoa, I mean, are we still talking about physics here, or are we going off the deep end?
Yeah, no, I think that was interesting. Well, when I learned it, it was already well known. Well,
Yeah.
it was known within I learned it from some popular articles on string theory. But
I mean, when did you start to actually work on string theory? What year was that?
Well, it's about 1990, perhaps.
1990. Okay.
Yeah,
Right.
I was doing my undergraduate, but I think it's interesting that in string theory, the equations of string theory are a little more constraining than the equations of general relativity, in the sense that they constrain the dimensionality of space-time, for example.
Which is a beautiful thing, except the constraint is not the one that perhaps we would have naively thought. Right?
Yeah, naively would have expected 4, but then in some sense comes with a gift that, what you were saying about, from the geometry of the internal dimensions, you could get various laws of physics. So it gives you more kind of opportunities to connect the string theory with reality.
Right.
So I guess in the 80s, it was believed that there would be a small number of possibilities.
Well, that's the thing. Exactly. When I was a graduate student, I mean, the original paper of Candelas, Horowitz, Strominger, and Witten had introduced how to curl up these extra dimensions into so-called Calabi-Yau manifolds, Calabi-Yau shapes. It only listed, I don't know, like 5 possible ways to curl up the extra dimensions. And so our goal was, if we can just find one other way of curling them up that gives rise to, say, 3 families of particles, quality of particle physics that was unexplained and still really is unexplained at the time, but was experimentally proven to be part of the data of the world. How exciting would that be? So we worked day and night to try to analyze the one example that Yau himself, with his student at that time, Tian, had put forward. And we thought, maybe this is it. Maybe this is the shape for the extra dimensions, because there are only a handful known. The problem, of course, is people found more possibilities for the extra dimensions over time. I mean, and the number grew over time, the number of possible shapes. Was that at all disheartening to you? Initially it was disheartening to me, but for you, because I'd worked so hard on one specific example, and you're like, why bother if there's so many, you know?
Well, yeah, in some sense, when I came into the field, the people had already found lots of examples, and this field had developed a lot and had become
You
really,
didn't have
really
your heart
complicated.
broken. You didn't have your heart broken.
Well, yeah, I didn't have my heart broken. I just was kind of scared by the amount of data that was already there in all this Calabi-Yau shapes, that I worked on some other aspects of the theory. So somehow the aspects that involve, well, what happens with black holes and
For sure.
other types of questions.
Yeah.
But
So I want to get to
I
that.
think it's still something that continues to confuse us today. So now there is, you could put a positive spin on this in the sense that you could say, well, if we have so many things, we can explain, small numbers and things like that.
Well, maybe we can spend a moment on that so-called anthropic reasoning, since you bring it up, because you're absolutely right. On the one end, you can say, oh my God, string theory just has too many possible universes that it might give rise to. On the other hand, if you're facing a number like the dark energy, which is this measured, well, indirectly measured quality of the world, that there's an energy suffusing space with a very strange amount, in appropriate units. It's like a decimal point with, a good, hundreds of zeros and then a one at the end of it, and we can't imagine how we could explain that from first principles, because most calculations start with 1 square root of 2 pi e thing. How do you get such a tiny number? But if you have perhaps a multiverse with many universes, each with a different value for the dark energy, well, somewhere out there, you're going to find the value that we've measured. So at least in principle, you have an explanation. Some people hate that idea, consider it a cop-out, or no longer doing science. What's your take on multiverse and using it to explain things that puzzle us?
Well, I think one point is that it's interesting that in string theory, the cosmological constant is calculable, or at least given some
another name for the dark
internal
energy
shapes. Yeah, you can calculate it. So it depends on these internal shapes.
Yes.
And I'm a little. I have some. Certainly, I find it logical that this is the way nature could work. That there might be some observer constraints, anthropic constraints. We have them in some aspects of physics. In biology, is super important. But in the problem is that it's a bit. It makes the goal of making a prediction more difficult, because it's saying that, well, there are all these possibilities, and then, okay, what we measure is just one of them, but it would be very hard to find that one, what precise shapes correspond to this particular one that we measured. So I find it a bit disheartening in the sense of it makes the task of finding an experimentally verifiable prediction harder, at least seem harder. Now we'll probably have to think more, and there will be perhaps correlations between parameters, or so that's
or maybe even
and that's probably one reason people hate it, that you say, well, okay, I explained everything. So but it's not I think it's not an explanation until you understand the theory well enough to understand what these possibilities really are, not just at the vague level, but at the more concrete level.
Yeah, I mean, and if we were one day, I mean, some people would say this is, an idle hope, but I think the goal perhaps is, if it so happens that reality does make use of a multiverse, it's a possibility. If there are many realms out there, our charge would be ideally to find some kind of way of predicting which universes are more likely. Higher measure is the language that we often use relative to others. Yeah. But it's a work in progress, like you're saying.
Yes, that's related. Well, we mentioned before this problem of predicting what happened in the beginning of the Big Bang, and there are a bunch of questions about quantum gravity in this regime, which involve predicting things that are constant in our universe. So if there are many different possibilities of our universe, let's say different possible values for the mass of the electron or the mass of the proton, so how do you assign a probability to each of them? Is it reasonable to assign a probability? And I think our current understanding of the theory does not allow us to calculate these probabilities. We fail kind of miserably when we try to. We get very confused and so on. So that's why I was saying that, well, string theory is a theory in progress. In principle, probably if we understand the theory well enough and we develop it well enough, we will be able to calculate these probabilities and then check whether they agree with what we see or not. But we are not only unable to calculate them, but if we make some estimates, the naive estimates, they're way off. So especially when we are talking about eternal inflation and such ideas.
Yeah. And so this certainly is an arena in which, look, I mean, in the most coarse language, one can say so far string theory has failed to provide
Mhm.
the mathematical apparatus to make definitive predictions.
Mhm.
This is the shape for the extra dimensions, or this is the likely
Yeah.
shape for this is the likely
Mhm.
particles that come
Mhm.
out of it, and so forth. And as you say, it's a work in progress. We just have to
Yeah.
own up to the things that still need work. In
Mhm.
fact, it's
Mhm.
exciting because the next
Yeah.
generation has deep things to work
Mhm.
on. Black holes, however, provide an arena in which string theory has made remarkable progress. I mean, if I was going to point to one area in which string theory has
Mhm.
really answered questions and in a way that I think many of us perhaps wouldn't have thought by the year 2023 we would have these kinds of insights. It is in the arena of black holes. And one of the issues there has to do with the so-called entropy of
Mhm.
black
Mhm.
holes, and this idea that Stephen Hawking and Bekenstein and others in the 70s developed, in this
Mhm.
idea that black holes have certain kind of qualities, degrees of
Mhm.
freedom, if you will, internally. And you can count those, as Stephen Hawking did, but in a manner that was a very delicate blending of general relativity and quantum methods. It kind of just skirted by using those two tools in a way that barely gets you to the answer.
Mhm. Mhm.
String theory has radically changed that, right? I mean, can you just give a sense of the work of
Right.
vast
Right. Right.
spectrometers?
Well, I think so. Let me say a little bit more about the history.
Please. Yeah.
So Hawking found that black holes have finite temperature, and then just the ordinary laws of thermodynamics implies that if you know the energy of an object, in the case of a black hole, that would be EMC squared, so the mass of the black hole, and you know the temperature, then you can, from these two things, you can calculate the so-called entropy, which is entropy. That is a thermodynamic object, and we know from Boltzmann and statistical mechanics that such an entropy should come from, in a quantum theory at least, or in a macroscopic theory, should come from the number of ways or states or configurations of the system. Um, so the black hole had to have this number of configurations, which would be very big. So because the entropy is proportional to the area in terms divided by this minimum distance that we were talking about before, called the Planck length. And so that works out to be a huge number for a macroscopic black hole. So it's an entropy much, much bigger than the entropy of any ordinary object of the same size. So it was mysterious because general relativity gives us just one black hole solution. And not
Yeah.
only that, but the black hole solution seems to be like an attractor. So if you perturb it a little bit, it goes over back to the same solution.
Yeah.
Um, so in the 1996, so Strominger and Baffa found some special black holes for which you could calculate the entropy by counting microstates. So they started with a certain black hole and changed the couplings of the theory, and then found some configuration of strings and brains, various objects whose number you could calculate very precisely. And it matched what you get using the Hawking calculation. So this was viewed as an amazing, and it's still an amazing
Totally amazing. Yeah.
result in string theory and consistency of the theory. So as you said, you started with the vibrating loops and this and that, and then you get this black hole entropy formula that was a mystery, since the 70s, when Bekenstein and Hawking first started talking about this. So it was really understood that string theory was doing something deep, and it was mysteriously consistent. And this type of calculations were refined and extended in various directions. And so, for example, you could calculate even corrections to the Bekenstein and Hawking answer, both from gravity and from this microscopic counting, and they agreed. And anyway, so whole story that is pretty amazing.
Yeah.
And then another development was trying to understand better sort of dynamics of black holes, what happens when you send something in, and how these various states kind of are changed and develop under time evolution. So in quantum physics, we have some states, and then as time evolves, you go from one state to another, and trying to understand this in more detail. And yeah, so that kind of led to this idea of ADS. The ADS-CFT correspondence, which is some way of understanding a bit more about the dynamics of black holes.
So before we jump to ADS-CFT, which is of course your great breakthrough, I just want to spend a little bit more time unpacking what you just mentioned, in terms of the entropy of black holes. So, it's kind of curious that the entropy is proportional to the area of the black hole, right? I mean, when you're talking about entropy, roughly people can think, the amount of disorder, as you say, the number of microscopic configurations that are compatible with the macroscopic qualities of whatever it is that you're studying. You would think that should be proportional to the volume of whatever it is that you're looking at, because more volume, there's more ways that things can be packed together. And yet it is proportional to the area. And that's telling us something pretty deep, which I guess is in its modern incarnation ensconced in the so-called holographic principles.
Right.
Can you say a couple words about that?
Yes. Yeah. So there seems to be a kind of dimensional reduction in the sense of where the degrees of freedom are. So if you think about the quantum field theory, so an ordinary theory that we use, for example, to describe particle physics, we think of those theories as having degrees of freedom, or let's say qubits, elementary quantum objects, per point in space-time. So there's an infinite number, but per point in space-time. So you would get a number which is proportional to the volume. The black hole entropy formula suggests this answer proportional to the area. So this prompted Toft and Susskind to say that in a theory of gravity, the basic fundamental degrees of freedom that we should use to describe any region of space-time should scale like the area of the region, not the volume of the region, as you naively expect in field theory. So that suggests that gravity is a fundamentally different kind of field theory.
Right. And I guess, the idea of hologram comes in because, a regular hologram, a thin piece of plastic, you illuminate it the right way, you get a 3D image from a two-dimensional flat piece of plastic. Here the idea is you describe, say, a volume in terms of degrees of freedom that live on an area that surrounds it. The area has one fewer dimensions because it doesn't have, say, the radial direction that goes within the volume itself.
Right. That's right. That's exactly right.
And so with Toft and Susskind giving rise to this notion of holography, that in a theory with gravity, the true degrees of freedom really live on this bounding surface as opposed to living point by point in the interior. You really gave that idea legs through the so-called ADS-CFT correspondence. I mean, if you could describe what that correspondence is, and then it's good to note how it takes this idea of holography and just makes it completely concrete.
Right. Let me try to say it in the following way. So you could imagine this surface being at the black hole horizon surface, but you could also put it a little bit further out, right? And still you would describe the interior, and you could put it even further out, and further out. And if you put it at the edge of the universe, so as far as you can, then you can say what kind of theory could live there. So you can give a more explicit description of such a theory. Because if you put it on the surface of the black hole horizon, it's a little tricky because some particles can leave the interior of the black hole to the exterior. And if you put it a little further, there's still some things that can leave. Sure. And it's hard to split space-time into two parts. If you put it very far away, then, well, everything is inside that surface very far away. And this works especially well in universes where there is a gravitational force that pushes everything to the interior. So this happens when the space is curved in a very particular way with constant negative curvature. And these spacetimes have a name. They're called anti-de Sitter. So de Sitter was a Dutch astronomer who considered a space with positive curvature, but these are spaces with negative curvature. And so they have a name. They're very simple, very symmetric spaces. And in these spaces, the main point is that the gravitational force pushes everything to the interior. So when you put the surface further and further out, the particles that remain inside, they don't get out. So it gives you a self-contained sort of box or system. It's like a gravity box. And then the theory that lives at the boundary is a theory similar to the theories we use for particle physics. So similar in spirit. So a theory of interacting fields that live at the boundary, or interacting particles that live at the boundary. So it's a bit like the universe. You could think of it as a crystal ball, where the surface of the crystal is the region very far away, and the interior is that whole universe. The idea is that theory that lives at the boundary can describe gravitational physics in the interior. And one important point I forgot to mention is that this theory that lives at the boundary does not have gravity. So it's a kind of quantum theory that we know how to describe very well. So it's a theoretically sound theory.
And so just to give a quick summary partway along in our discussion, you're claiming that if someone lived on the surface of the crystal ball, way out there on that surface, say at the edge of the universe, and they were doing all of their analysis using ordinary quantum field theory without any gravity, they would give a complete description of everything that a person in the interior of this universe would come to using a theory that has gravity. So it's like two distinct descriptions. One uses the ordinary tools that we have developed over the course of many decades, tested at least the framework, not the exact theory, but the framework within things like the Large Hadron Collider, and it gives answers that would be completely the same, prediction by prediction, as say a string theory with gravity in the interior of that.
Yeah, that's the idea. So the idea is it's a conjecture, and it's a conjecture partly because the string theory in the interior, the theory of gravity, is not completely well defined. So as we saw, it's a theory under construction, and we know all the things that we can calculate, they agree. The things we can calculate on both sides, they agree. So it's a conjecture, and we don't know how to prove it in complete generality.
But case by case, it comes through in every calculation that anyone's ever done.
Yeah. So you can calculate consequences. So you can consequences mean that there are some calculations you can do in one theory and calculations you can do in the other theory and compare the answers. And it's the agreement is amazing. People have done many calculations, and they found agreement.
And by many, I know you're too modest to say, so I hope you don't mind me jumping in. I mean, there have been tens of thousands of follow-up studies of the conjecture that you put forward. I guess it was 1997, 1998 was when the first paper was written. And every single one of those tens of thousands of follow-ons only gave more evidence for the conjecture that you put forward. Right. So it's widely believed in the field that this is true for that reason. So I wanted to drill down a little bit on its implications before going far. But did you want to go give anything further on the basic idea itself?
No, let's discuss some implications.
Yeah. So there's so many directions that one can go, but I can't help but ask one, which is, we started out in our discussion of string theory noting that it's really tough to test string theory. And we didn't say at the time, but perhaps we should say it's tough to test any theory that puts gravity and quantum mechanics together, because the place that you mentioned early on, the moment of the Big Bang or the center of a black hole, these are such extreme environments that we don't have direct access to. So it's just hard to test a theory that really comes to life in such an extreme domain. But I'm wondering the following. Once you realized, and once the physics community gave more and more evidence for the likely possibility that string theory is not as different as we once thought, it's not as radical a break as perhaps we once thought from previous ideas, because, as you just said, you can describe string theory in one realm by quantum field theory, just in a different realm. Does that, in your mind, shed slightly different light on the question of experiment? Because the framework of quantum field theory has been tested to fantastic accuracy, at least for certain field theories. Doesn't that perhaps shed a nice glow on string theory in that it becomes much closer to experiment than perhaps we once thought?
Yes, yes. I think one direction that I think is very exciting is the following. So this field theories that live at the boundary, or more general quantum systems, they are strongly interacting. So they need to interact very strongly. And one exciting possibility is that we could somehow artificially manufacture in a lab some strongly interacting quantum system that might have one of these emergent gravity universes. It wouldn't be a very big universe. It would be just small, a few Planck lengths. But it could be a universe that might be meaningfully described by gravity. So you would, in your lab, arrange a bunch of atoms and make them interact strongly and so on, and then predict its behavior, their behavior in terms of solving Einstein's equations in some universe. It might be a higher dimensional universe and so on. And so you would be creating a phase of matter or some matter configuration that really is being described by gravity. I think that's very exciting. I think it's exciting first because it might teach us new things about gravity, because we might simulate this and ask. We will be forced to ask new questions about gravity. We might experimentally see some gravitational phenomena that we will then discover how to describe theoretically and see exciting results.
Do you think it's likely
now, let me ask? So how difficult is this? So
exactly.
One can do an estimate. So there is there are various examples of this ADS-CFT type situation. So you can look at the simplest one to simulate, and you can estimate what's the smallest number of qubits that you would need to have something that you can describe by gravity. And people did some, Hanada and collaborators did some computations using an ordinary computer of the entropy of these systems, and they found that with about thousands of qubits, it would be enough to get results that match gravity. Now, this number is more or less the same number of qubits you would need to break the codes, the usual RSA, the usual, usually when they say quantum computers will, break the codes we use for internet communication and so on. In order to really practically break them, you need to have about 7,000 or several thousand qubits, and the number of operations you need to do is also comparable between the black hole example and this example of the breaking of codes. So if quantum computers live to their promise of revolutionizing cryptography, then they will also revolutionize, I think, quantum gravity.
Yeah, no, that would be utterly remarkable, fantastic.
I don't think it will happen anytime soon, but I think maybe in 30 years. So if you extrapolate,
so that would be a sort of wonderful, way for this theory to develop. Let me get your thoughts, though, on another potential connection to experiment that people are becoming less optimistic about compared to perhaps the way they were some decades ago, which was to find the so-called superpartner particles. That is that would reflect the supersymmetric quality. The super in superstring theory is supersymmetry. It's as many in the audience no doubt know, it's a very abstract symmetry principle that was really discovered by physicists who were studying string theory. It was then generalized and applied to ordinary quantum field theory as well. One implication of this symmetry is that for every known particle, there should be a partner particle. For the electron, the selectron, quarks, squarks, and so forth. And I certainly had high hopes, as I think most, but not everybody in our community did, that the Large Hadron Collider, after finding the Higgs boson in 2012. The next discovery that was going to be right around the corner would be the discovery of the superpartner particles. And that has not yet happened. Is that discouraging to you, or were the ones who wasn't expecting success on that in the first place?
Well, I was a bit disappointed, but in the following sense that the simplest theories we can understand are supersymmetric theories, supersymmetric string theories. And if supersymmetry had been discovered, then we would already be in the realm of the things that we already understand. The distance, the number of powers of 10 in between the Planck scale and the scales that we can measure today is very big. So supersymmetry might be broken anywhere in between. And so it didn't have to be discovered. It would have been nice if it was discovered. And one reason for expecting it at the LHC was because of it would offer a natural explanation for the value of the Higgs mass.
Yeah.
Now we know that there is no new particle, no supersymmetric particle, so the value of the Higgs mass is a bit of a puzzle. There might be physics at higher scales, maybe even be supersymmetry beyond the scales of that can be measured by the Large Hadron Collider that might explain or help to explain it. But it's not a completely natural value in some sense.
Yeah. Now, we should quickly say that we don't know for a fact that supersymmetry, it's not like supersymmetry has been ruled out. It's just become less likely because the parameter space of possibilities has been shrinking as experiments have gone forward. But
I'm not sure it's very less likely as a fundamental symmetry of nature. It could be.
Yeah, I agree with that.
Maybe equally likely. It's just that it's not at the scale of the LHC. Maybe we'll have to work to the next accelerator. Maybe it's many more much higher scales.
Yeah. And do you mind if I spend
focus? Yeah.
Can I just for folks to understand the point that you just made, which is a very important one? Supersymmetry, the symmetric quality, could still be a quality of the underlying equations, the underlying mathematics. It simply could be that it doesn't manifest itself at energy scales that we can currently access. As you're saying, you just may need a more powerful machine, and maybe ultimately, if it's powerful enough, you can access the particles that the symmetry requires to be there.
Yes. I mean, it's also possible that there are other theories of quantum gravity or other regimes of even the quantum gravity theory we know that are not supersymmetric in.
For sure.
It's also possible. So people are trying to understand quantum gravity sort of in trying to extract lessons from string theory that might help us build a perhaps more general theory of quantum gravity, more all-encompassing one.
And you mentioned other approaches. Now, of course, I know that you were referring still to the universe of ideas that swirl around string theory. But if we just take a small diversion for a minute or two, there are other approaches that people have developed for putting gravity and quantum mechanics together. Dynamical triangulations, perhaps loop quantum gravity is the one that may be most familiar to people who are watching this. There are books that have been written about it for general audiences, and some of its proponents are out there making clear that they think that their approach is perhaps the one that should be gaining more attention than string theory. What do you think about loop quantum gravity? No holds barred.
Well, I think it's an approach that is based essentially on a canonical quantization of gravity from 2 to 3+1 dimensions and trying to solve all the constraints of GR.
Yep.
But I think it's not as developed. It's not as developed, let's say, as string theory. Maybe there might be developed in the future, but it does not reproduce some very basic things like Lorentz symmetry in 4 dimensions or higher dimensions, and how gravitons scatter, gravity waves scatter with each other. You like to be able to calculate this. You can do that in string theory. You cannot do that in this theory. Black hole entropy, these calculations of black hole entropy, apparently gives, maybe you have to put in a new parameter to adjust it. So
Yep.
it's not as developed and as clear. So now, I think in the history of, let's say, string theory, there were sometimes things that were viewed to be outside string theory. I think a very good example is 11-dimensional supergravity.
Yeah.
So there was a time when there were a group of people studying 11-dimensional supergravity, and then there were string theorists at the same time, and the string theorists saying, well, what you're doing doesn't make sense because this theory is not normalizable, it's not. And eventually it was understood that this 11-dimensional supergravity is related to string theory in some way. Yeah, so that's an example where an interesting idea that seemed maybe not exactly right, but then it was incorporated in our more modern understanding. And like this, there were other ideas like this. And yeah, maybe something like that will happen with these other approaches, that eventually there might be some element that will be put into more, it will be used in some way, and it will find the right place in our theoretical understanding. Yeah.
Now, it's very diplomatic, and I try to say similar things when I'm put on the spot that way with somewhat unfair question. I mean, even roughly speaking, loop and loop quantum gravity, it sounds like some kind of string-like shape, so you can't help but hear the resonance between the words. But yes, in detail, it seems at the moment that the theories are quite different, quite distinct. But who knows? Like you say, maybe one day we'll find that there is some way that these ideas contribute maybe to even a third theory that we've yet to even come up with. And in the best of all worlds,
yeah. Well, there are some ideas that people are discussing now. Something called tensor networks, which is some way of originated some way of describing complex quantum states, and now people are thinking about space-time in terms of this tensor networks as, for the moment, mostly as a qualitative idea. And there is some vague similarity with some of the ideas of loop quantum gravity. So I think, maybe that might be the way. There might be a connection.
So there are three other quick things, if you have time to briefly talk about them, if that would be all right. So, some years ago, and I no doubt some of our audience have read about the so-called, firewall paradox that emerged when people were thinking about black holes and trying to square our understanding of black holes with our understanding of quantum mechanics, most directly understanding our understanding of quantum entanglement, the fact that, widely separated objects can be somehow connected to each other. And there was an issue that arose in these ideas, creating quite a lot of tension in thinking about black holes. Can you just give us a sense of what the issue was and perhaps even where we stand now in the issue?
So I think the issue has to do, it's a version of the Hawking information paradox. So that we think that if we are sitting outside a black hole and you send in particles, the Hawking radiation should carry the information that was initially contained in these particles. So that's what we think if we think about, for example, ADS-CFT, or we think that we should have a unitary description as seen from the outside, or a description according to quantum mechanics as seen from the outside. But on the other hand, in general relativity, that matter that fell into the black hole is still in the black hole interior somewhere. So you have on one hand information inside the black hole interior and also the information that is coming outside. And in quantum mechanics, this is not possible. So you're not supposed to copy quantum information. So it's so-called the no quantum xeroxing principle. And so that's roughly what Hawking's problem is. And here they translate the firewall paradox was really a paradox that translated this problem into something a little more measurable. So where an agent would collect the Hawking radiation that comes out of the black hole and would distill some quantum bits that are entangled with the bits that the black hole will emit in the future. And then someone could take that distilled qubit and fall into the black hole and check some impossible pattern of correlations of entanglement. And so that was the paradox, and it was called firewall because that was a particular proposal that they had for how to solve it. And I think nowadays we think it would be solved in a slightly different way. So but in the process, rather than giving you how we think it's going to be solved, I would say that in the process of analyzing these questions, we understood better the connection of quantum entanglement and gravity. And also, there is something that we said in the beginning, that so if we sit far away, we can describe all the space-time, all the space-time inside. This turns out not to be completely right, in the sense that you can describe all the space-time, perhaps including part of the black hole interior, but in some circumstances you cannot describe the other part of the black hole interior.
Right.
So the limits of what you can describe from outside were more properly understood.
Right.
And this involves, one of the key, let's say, workhorses in developing this new understanding was a new formula for black hole entropy. And this is, I think, something very important. Which is somehow similar to the area formula of Hawking and Bekenstein, except that it's not the area of the horizon, but it's the area of some minimal area surface. And this formula is very exciting because it gives us not the thermodynamic entropy of the black hole, but the so-called quantum entropy of the black hole. So the real total amount of information that you get, even if you do arbitrarily complex measurements. So it's a kind of more precise and sometimes called fine-grained entropy measure. Sometimes also called the quantum information measure, and so on.
Yes.
So it's really getting at the heart of what quantum information is contained in the black hole. And it crucially depends on the geometry of the black hole interior. So the Hawking-Bekenstein formula doesn't care about the geometry of the interior, only the geometry outside the horizon. But this formula really cares about the interior. And in certain cases, that entropy might be very small. In some cases, might be large, and so on. And in this process of taking a surface and minimizing the area of the surface, you sweep somehow a region of space-time that includes the outside and part of the interior. And this whole region is supposed to be the one that is described by the theory outside. And so it gives us that region of the geometry. Now, what is described in the other region? And the idea is that other region is described by whatever is entangled with the black hole. So if you have a black hole entangled in some quantum state with something else, then that other region is described by something else. So this gives this interesting new picture. I think it's a generalization of the previous sort of ADS-FT discussion, in the sense that you could have separate quantum systems, each describing a portion of some geometry, and the geometry could be completely connected, but each side is separate, and we have a quantum state that is entangled among the two sides.
Yep.
And somehow it looks as if this entanglement generates a geometric connection in the interior of the black holes. So that's
and a closely related set of ideas that you've also developed has to do with the connection between, as you mentioned, quantum entanglement, and gravity through its geometrical incarnation. That is a connection between two papers that Einstein himself wrote in 1935. The first, of course, is his EPR paper that used entanglement as a weapon against quantum mechanics, trying to argue that it said that quantum mechanics was not complete. Most people now interpret it not as an actual undercutting of quantum mechanics, but shedding a bright light on one of the wonderful qualities of quantum mechanics, namely quantum entanglement. In 1935, he also wrote a paper on wormholes with Nathan Rosen, this idea that there can be shortcuts in the fabric of space-time between one location and the other, kind of tunnel through the fabric of space-time. Your work suggests strongly a connection between these two papers that Einstein himself was not aware of. Can you give us a feel for what that is?
Right. So this Einstein-Rosen paper is a paper on basically a paper trying to understand better the geometry of the Schwarzschild, of the solution that
Black hole
Schwarzschild
solution.
found. Yeah, and what they discovered is that the geometry really connects two separate universes. It's somehow a connected geometry, kind of wormhole, as you said, between two universes. But it is really not traversable wormhole. So it's something that you cannot use to send signals. And the idea is that this geometry should be viewed as two separate black holes. So they have two universes, two black holes in each universe, but the quantum states of these black holes are entangled. And that entanglement creates that connected geometry. So that's the idea. And this idea has been made more precise using this entanglement formulas. The original formula was due to Ryu and Takayanagi and was improved by many other authors. And so now we understand a little bit better how this works.
I mean, would you? Is it too coarse to say that whenever there is quantum entanglement, there's some kind of wormhole-like geometry?
Right. Yeah, at the level at this time, I think it's too coarse to say this. So the thing is that it depends on what you call geometry. If by geometry you understand a big space described by Einstein's equations, then the answer is no. It's not true. So it's only particular patterns of entanglement correspond to those geometries, but not anything.
Of course.
Now there is an open question, which is, well, is there a generalization of geometry where this would be true? But we don't know that generalization.
So final thing that I'd like to just spend a moment on, when string theory came along, it suggested a revision to some aspects of space-time. For instance, as we discussed, the number of dimensions of space was increased from the naive value of 3 to, say, 9 or 10 spatial dimensions, depending on whether it's string theory in the original incarnation or the M-theoretic 11-dimensional supergravity that you made reference to earlier. String theory also suggested that these extra dimensions would have a rich geometry curled up into some strange shape called the Calabi-Yau shape that we also made reference to earlier. Are we going further right now? Is string theory and our work in quantum gravity more generally, is it suggesting that space and time, or space-time itself, is not a fundamental ingredient in the nature of reality and instead should be thought of as some kind of emergent feature that only really is relevant in certain environments, but more fundamentally, we should be able to talk about physics in the absence of space and time?
Well, I think in this notion of ADS, CFT, or these dualities, at least some directions of space, or maybe all the directions of space, are emergent in the sense they are not in the fundamental description. That involves some qubits, for example, and then you make the qubits interact with each other, you get some higher dimensional space. We don't have good examples where we have emergent time. I think the interior of a black hole is a situation where we have some kind, the time direction in the interior is in some sense emergent, but we don't understand it well enough. So that is part of the things we don't understand, and hopefully we'll understand them soon. And yes, it looks from this description that the quantum mechanical description is more fundamental, and the space-time looks like subordinate or emergent. What is emergent is certainly the space-time that is governed by Einstein's equations. So that only arises in certain circumstances. Now, the string theory description is a description that uses this space-time and maybe some modification of that space-time. So it suggests that there might be a theory that generalizes the notion of space-time, from which maybe the boundary theory might emerge, or whether. So I have not given up on a theory that is described involving space-time, or some generalization of space-time, such as the one we have in string theory.
But
Um,
once you have duality, once you have duality, say ADS-CFT,
mhm,
where you've got these two distinct descriptions,
right,
one say involving one fewer spatial dimensions than the other. So
right,
the geometrical settings within which the quantum mechanical, the quantum field theory description is very different from the geometrical settings, say in the gravitational and the string theory description. Is that enough, perhaps, to say that space at least is not fundamental? Because if it is, which one would be the fundamental description? Isn't it quite clear even at that at that dual description that you've entered a realm
mhm.
where the fundamental ingredients are no longer describable in terms of a space-time?
Um, well, it could be that if you have the interior space-time and you sum over many space-times, or you consider the full quantum theory of those space-times, then you might get the same answer. So it's a bit like so-called Fourier transform, which is a way we
Sure.
have of representing signals. So you can give how the signal changes in time, or you can give all its frequency components.
Frequencies. Yeah.
And we know that if we are describing a signal, you can give either of these two descriptions, and they would be equally valid. And so it could be. I think it might be something similar that we can have either any of the two descriptions might be valid, and we'll
Right.
at
So you're
some point
saying
we'll.
if we use the full quantum description on the quantum
Mhm.
side and summed over all
Yeah.
of the geometries,
Mhm.
perhaps it
Mhm.
all blends together in a way that yields some unique geometrical description, at least in principle.
Right. Right.
Yeah. No, no,
And yeah, and there are some very simple examples in 2 dimensions where something like this is being done. I mean,
sure.
it's done, and you get some sort of boundary description.
Yeah. So final question here. I mean, I've been fiddling, playing, working on these ideas, since 1984, 85. You've been doing, as you mentioned, since 1990.
Mhm.
Are you happy with where developments over the last 30 years have taken us? I mean, have we gotten as far as perhaps you would have hoped way back when you were starting out in 1990?
Um, well, I certainly hope we were further along. That we had. I would hope that we would have an experimental prediction that we can
Yeah.
measure and test, and some prediction for cosmology, perhaps. And on the other hand, I think that there's been a lot of progress. Things that looked impossible or out of reach are having, like, well, especially in this black hole area. Um, Certainly, or even regardless of black holes, understanding strings at very strong coupling and so
Yeah.
on. So there were many things that were definitely mentioned as very important open problems in the 80s or early 90s, and now have been understood. And
Yeah.
I hope the same will happen with the problems that we are now discussing, like the interior of black holes. I think that's a problem that
Sure.
hopefully there will be much more progress. And I think there's been some progress through these entropy formulas, and we'll hopefully see more in the future.
So overall, optimistic?
Yes, yes, I think it's an exciting area, and well, it's a long shot in the sense that it's a very ambitious program. I think it's leading to interesting formulas, interesting mathematics, interesting new ideas. I keep hearing new interesting ideas, so that I can't even keep up with the interesting new
Yeah.
ideas people are proposing. So it's the field is moving, and yeah, I think there will be.
Yeah, and in the end, that's the right barometer. A theory that gets stuck ossifies. It doesn't change. It gets set in stone. String theory is this malleable, rapidly developing, extremely exciting collection of ideas that ultimately we hope will coalesce into one full understanding of this theory. And getting back to our initial questioning, give us an insight into the nature of the Big Bang and how things really began, or to the deep interior of a black hole. So I think that ultimately is where we are heading. So Juan, thank you so much for the time
Sure.
today. It was a fascinating conversation on everything from Einstein unification to black holes to holography to ADS-CFT to duality to the emergent nature of space-time. So It's been a pleasure speaking with you, and thanks so much for joining us.
Yeah, it's great talking to you, and well, greetings to everyone listening.
Excellent. Thank you.
Bye-bye.
All right, everyone, that's about a wrap here in our conversation with Juan Maldacena. A real rapid tour through the last, really, we went all the way back to 1968 for a moment. So over 50 years of development in string theory, which remains a vibrant, exciting, fast-moving field. And we just have to recognize that certain questions that we'd hoped to have answered by today, like a definitive testable prediction that we just go out and see whether or not these theories are borne out by datas, we'd hope to have that by today, but we don't. But we're still working hard to get there. But we have gotten insights into black holes, the nature of space-time, and the deep connection that Juan is responsible for between our understanding of gravity on the one hand and a theory without gravity, but with quantum mechanics, namely a quantum field theory on a bounding surface of an interior space-time, is such a remarkable and powerful insight that it really has set the course of string theory research over the course of 20 plus years. And we suspect that this is a key to understanding the true nature of space, time, gravity, and matter. So only time will tell where all this will go, but it is certainly a fast-moving and exciting field. If you're interested in more on this subject, please subscribe to our YouTube channel. We had another live discussion here in New York City with a number of leading string theorists, Ed Witten, David Gross, Andy Strominger, where we covered somewhat similar ground as we did with Juan, but it's great to hear a variety of opinions on the developments that have characterized string theory research over the past 30 years. We'll be releasing that program, I don't know, probably in the next few weeks, I think. We're also going to be releasing a program on artificial intelligence that we did at that live event in New York City, as well as a whole series of other programs, as well as these live conversations. So if you want to know what's going on, please subscribe both to our YouTube channel and also to the World Science Festival newsletter, so you will be alerted when these programs are both live and become available. All right, that's all for now from New York City, Columbia University. Brian Greene for the World Science Festival. Thanks for watching.